Allô, vous m'entendez? C'est parfait. So hi, I'm speaking English today. My name is Benoit Spolidor, and I'm the head of AI for the Guild in France. Before we start this amazing opportunity with Kian to learn more about deep learning, I have a couple of announcements. If that works. So the first one is that it's presented by the Data Science and Artificial Intelligence Guild. So we are a community of experts in data science and AI. And so you're very welcome to join us or post questions or Yammer if you have any questions. We're here to help you. The guild is managed by myself for the AI part, and by Thierry Vauclair for the data science part. So I don't know if Thierry's here. He's not here. That's too bad. The second part, it's we're announcing the launch of our deep learning platform, which are here with Michel Sebag. The training is going to be starting soon, so if you have any questions about the deep learning platform, please ask Michel Sebag. And finally, I would like to really thank the following people for their help today, organizing the events. Without them, it wouldn't be possible. I mean, it wouldn't be possible. We would be on the 4th floor in a small room by myself. So thanks to them, we're here today with a bunch of people in this cool room. So for the events, first Kian is going to be doing this presentation for about an hour, and then we'll have a Q&A session. But if you have any questions, please don't hesitate to interrupt Kian during his presentation. As you notice, we're speaking English right now, and that's because this is being broadcast live to our friends in Europe, in the UK and Germany. But do not hesitate to ask questions in French if you rather speak not English. What else? We have a cocktail afterwards. So now, some people at ITA have had a very big party this weekend, so for them it's a way to keep on partying. So for now to introduce Kian. You know, as they say, there's a saying in English that says that when you're the smartest person in the room, then you are in the wrong room. And I think today at Soprasteria we're all in the right room, except Kian, basically. Kian is, despite his young age, he's 12. He's both already a leader in the AI field, both academically and professionally. Academically, he's a graduate of École Centrale Supélec and Stanford University Management Science and Engineering. He's now a lecturer at Stanford University along with Andrew Ng. He's an advisor. Andrew Ng was one of the foremost experts in AI. He's co-written the Coursera course on deep learning along with Andrew Ng. And he's the recipient last year of the 100 Gigawatts Award, which is the most prestigious award in teaching at Stanford. And professionally, he's had his own startup already, and he's now working with Andrew Ng on a couple of new startups, Landing.ai and DeepLearning.ai. You can maybe talk more about this later. So, this is for me. I'm again actually proud to have Kian here present us his work in deep learning, and I will now give him the microphone. So please give him a very, very warm welcome. Thank you.
Thank you, Benoit, and hi everyone. I'm really excited to be here. It's been 3 years since I left France, and it's always good to be back, and even better at La Défense with you guys in Sopra. So, as Benoit said, I'm going to take questions during the presentation, but also after, so feel free to stop me. If my pronunciation is not good, so that you don't understand, you can stop me as well. Or if you have a follow-up questions. So we're going to start with a small introduction, just to have everybody on the same base, around deep learning and neural networks. Just to check in, how many of you have taken the deep learning specialization on Coursera, or have taken part of it? Okay, so we're going to have this intro, where I'm introducing you what neural networks are and how we work with them. And then, after this intro, we're going to see practical applications. And it's going to be across fields, so if you have a question about what you can use in your field from the neural network, just stop me and ask. Okay? Let's go. So the first thing is you can think of machine learning and deep learning in general as a black box, where you will have something going in the box and something coming out of the box. The box, we will call it the model. And what's going in, we can give an example that is a cat image. It can be something else, we'll see later. But let's say it's a cat image. We give a cat image to this model, and it gives us an output. It's a number. In this case, what we want to do is to detect if there is a cat on the image. So the output of this box is going to be a number between 0 and 1. That's going to give us the probability of the appearance of a cat in an image. So we expect this probability to be close to 1, right? Because there is a cat on the image there. Humans are very good at this task. And I'd like to simplify and call the model two things. A model is an architecture plus parameters. So the architecture, we're going to see what both of these are. But when someone talks about a deep learning model, an AI model, a machine learning model, it's usually an architecture plus some parameters. The architecture we're going to talk about today is neural networks. And the parameters are just matrices of millions and millions of numbers. So just as simple as that. Millions of numbers in your computer, this is the model. And these numbers are mimicking the task of detecting cats in an image. The problem in AI is that we don't know what's the function that makes us understand what a cat is. We don't know this function. If I ask you to write it, you won't be able to write it. Or tell me if you're... and in order to find what's this function, we're going to fit an parameters on this architecture and understand what it is. So now we can sum up this thing as find the function f, that is the model, such that f of the image equal 1 if there is a cat, and 0 otherwise. Does that make sense to everyone? Okay. Now, how to find the right model? This is the whole optimization problem in machine learning and deep learning. We're going to quickly see it. I will start by fixing an architecture. Let's say I'm going to use neural networks. Then I'm going to initialize my parameters randomly. It means all these numbers that we have on our computer, we have to start from some numbers. These are random at the beginning. And little by little, we're going to find the right numbers by changing them slightly all the time. How do we change them? This is the optimization process. Who's familiar with some kind of optimization here? Okay, so you're familiar probably with gradient descent or other type of optimization algorithms. Great. So let's say we give to this problem a cat image. Okay, the cat image was lost, but there's a cat image here normally. Imagine there is a cat image. Because there is a cat on the image, we know that the label of this image, so the ground truth that the function should output, is 1. Now we will give this cat image to the model, and it will come out as an output. And this output is going to be wrong, because our parameters are random, right? These things are totally random. So what's coming out is not 1. The algorithm doesn't understand that there's a cat on the image. So we're going to tell the algorithm that, okay, you're very wrong. We're going to compute the difference between this number and this number in a certain way. It's not exactly the difference, but it's a metric of distance between the probability output of the model and the ground truth output. And we're going to tell our model. We're going to compute what we call a loss function. Who has heard loss function before? Okay, so I'm going to go quicker here.
Can you tell maybe what the loss function is and the gradient?
Yeah, perfect. So a loss function, also called an objective function, is the function that you want to minimize. So it means it has to represent the difference between what your model does and what you want it to do. Okay? What you want is this difference to be very small. You want the model to do almost what you want it to do. Right? And in order to do that, you will compute a gradient. You know what a gradient is? So for some of you know derivatives. Oh, I have a brand new one, no? Yeah. So let's take some seconds to talk about the loss function. So let's say the ground truth is y, the number y. So this is 1 here. Okay? And the output probability of our network is y hat. This is 0.05. What we want is this distance to be minimal, to be as small as possible. So we will call our loss function y minus y hat. We want this to go to 0 as we train the network. In order to go to 0, we have to do an update on our parameters. So let's say our parameters of the model are called W. Right now, W's are wrong. I want them to be right. So what I'm going to do is that I'm going to update them at every step. I'm going to set them to a certain value, that is this value. Does that make sense to everyone? Okay, so this is the gradient derivative of the loss. It tells us how much we should move the parameters W in order to move the loss function L. And I put a minus sign here because I want the function L to go down. Okay? And this is called the learning rate. We're going to talk a little bit more about it. Okay. So, forward propagation means I send the cat in the model, I get a number. Backward propagation means I do this loop. I compute the distance between these two numbers, I update my parameters, and then I give another cat to the image. It's going to give me another number that is probably going to be closer to 1. And I'm going to do that several times with many, many images. And this is what we call data sets. It's a bunch of images of cats and non-cats, and I'm going to do that for all of them until my parameter understands what a cat is and what a cat and what not a cat is. Does this process make sense? So this is basically the gradient descent optimization algorithm. There's a bunch of other optimization algorithms. We're not going to talk about them. What's interesting here is that there's a bunch of things we can change in this process. We can change the input. What kind of input do you know? Or do you deal with on a daily basis? Text input. This is a field called natural language processing usually. Any other ideas? Audio. So audio is usually sequence signals that are sounds, and it's also called speech recognition or speech verification or things like that. Any other? I'm sure you all worked with the CSV file that was very ugly, and you had to clean it and then get it. So this is another type of data, it's raw numbers. Output can change as well. In this case, we're in a classification task. It means we want to output a probability to tell us if something is happening or not. It's binary. It's binary classification. It could have been a regression task. For example, if you predict the price of a house based on some features such as the size of the house, the output is a real number, which makes the task a regression task. Okay? We have a bunch of different tasks. The loss function here is a certain loss function that is called L1. But we're going to see a lot more loss functions today. And I think the core part of machine learning is to choose the right objective function to minimize. This is a very important part. Finally, the architecture. You've probably heard of convolutional neural networks that work very well on images, recurrent neural networks that work very well on sequences, and fully connected neural networks that work on other type of tasks. We're going to see all that together. And also, initialization can be totally different. So there's so many things we can change. And this makes it a little harder in deep learning. Now, you probably know that an image in computer science is numbers. It's a 3D matrix that we call RGB because there's a red channel, there's a green channel, and there's a blue channel. Now we're going to take all these numbers, put them in one vector. Here's the vector. Okay? And I call it x1, x2, until xn. I'm going to give all these numbers to a unit that is called a neuron. Here. It's a simple computational unit that has two parts, a linear part and a sigmoid part, which is an activation function, and we're going to talk about that later. It makes sure that the number here is between 0 and 1. Okay? Now, I give the cat image. If the network is trained, it should give a number that is closer to 1 than to 0. Then I will threshold it, and I will get it's a cat, because this number is more than 0.5, which is the middle between 0 and 1. Okay? This is called the logistic regression. It's the simplest neural network you can think of. It's a neural network with only one neuron. Now, let's say I ask you to do the same thing, but for 3 animals. I want to detect giraffe, elephant, and cat on an image. How would you change that? Yeah. I heard the answer, I think. Tree model. You could have 3 models. It means you could do that for cat, you could do another one for elephant, you could do another one for giraffe. What's the downside of that? You can add 2 neurons. Yeah, so the downside of having 3 models is that every time I have an image, I have to run it 3 times, right? And then I would probably take the highest probability. But this is not what we want to do. We want to have 3 neurons. So what I do is that I just add 2 other neurons that are other computational units. And these neurons are going to be responsible to detect what a giraffe is, or what a dog is, or what a cat is. Does that make sense? And now, talking about the parameters. The architecture is this thing. The parameters are these things. W, W, W. You can think of all these edges as being one parameter. This edge is the parameter that is going to multiply this pixel, because this is a pixel value. It's going to multiply it, and it's going to tell us how much it thinks there's a cat or another animal in this pixel. Okay, now, if we want to solve these 3 animals, how should we label our data? In the previous slide, we said if we have a cat image, we want to label it as 1, because we want to say there's a cat on this image. If there was no cat, we would put 0. In this case, we have many animals we want to detect. How do we label our data set? Vector probability? Everybody agrees? Do we label with probabilities? If I give you an image, let's say, with a dog, no cat, and no giraffe, how you label it? Yes? 1, 0, 0. So it's not exactly probabilities. It's 1 and 0s. It's called a multi-hot vector, or a one-hot vector if there's only one. So if there is an image with a giraffe and a dog, it's not very common, but I would have 1, 0, 1. So I would tell my model, take your probabilities here, use your loss function, and update your parameters based on what the label was. And I do that all the time. Okay? Does that make sense? So, now the notation we usually use is this type of notation. This is called a layer. As you probably heard that deep learning or apprentissage profond is a lot of layers. And this is one layer. And the layer, we call it 1. It's the first layer. The number here on the bottom is the neurons index in the layer. And A stands for activation, which is another thing that we can tweak. Okay? We can even stack layers to make the network more and more complex. Does someone know why we would stack layers? Why is it interesting to put more and more neurons? Yes? Exactly. It's better in order to extract more complex features. So it means that, let's say this neuron earlier, let's say we were still on a cat classification task. We want to detect cats on images. Usually if you use a very deep network, you will find that earlier neurons are going to detect edges. They're going to detect simple things. They're going to see only the pixels coming in, and they're going to tell us, okay, these are the edges of the pixel. Now, they're going to communicate this information to the next layer, right? So this one is going to tell, I've seen an edge here, and it's going to tell it to everyone. This neuron is going to say, I've seen an edge there, and so on. So what comes in the second layer is better information than what comes in the first layer. This neuron is going to receive all the edges, and is going to be able to say, oh, this is an eye. Is an eye, probably. This neuron is probably going to say, this is a mouth. And then, they're going to send this information to the last neuron, which is going to take the mouth, take the eye, take everything, and understand that there is a face here, or face of a cat, or in this case, face of a human. So this is what is extracted from the network after training it. That's what we all do. Okay, so it's better to have deeper networks when possible, because it allows us to extract more useful information the deeper we go. So now, if I give you a network that was trained and I ask you, I give it a cat image and I ask you, give me the edges of these cats. Where should you look at in the network? Yeah, probably the first layer. If I ask you to tell me if the network has seen the face, I would ask you to look at the last layers. Does that make sense to everyone? Is it too fast or too slow or okay? Too slow? Okay. Okay, it's going to be more complicated after. So this is called encoding, this technique, encoding values. We're going to talk about it a little more. So let's build now what we've learned on concrete applications. And what we're going to do is that we're going to have a first part on practical applications of deep learning, including day and night classification, face recognition, art generation. Maybe if we have time, we'll go on the deployments. And then we'll do a case study on trigger word detection. And then I'd love to talk with you about what you guys think is an AI company. What makes a company an AI company versus a non-AI company? Okay? So let's start with day and night classification. Our goal, and we're going to do it together, is that given an image, tell me if this image was taken during the day, 0, or during the night, 1. First thing we should do is to think about the data. Can you guys tell me what data we should build? What data set should we build? Okay, images taken during the night and during the day, and we would label them 0 and 1 based on when they were taken. Sunset and sunrise, why do you need sunset and sunrise? Exactly, so these are the hard examples. Sunset and sunrise, probably your model is not going to find it at the beginning, but then you would bring more data until it finds it. What other type of pictures should we gather? Indoor. Yeah. Like if I take a picture here with a little hint that there is a window in the back, do you think the model is going to find out or no? Only if you've given images like that. So this is very important. Because for a human, it's pretty easy. The human will focus on the window, and that's all. The model, you have to teach it. You have to teach it a lot, very slowly. Okay? So yeah, I agree. It's going to be a lot of images. And by a lot, I mean 10,000. You agree with 10,000? How did I choose this number? Experience, probably, yeah. You build several models until you get a sense of how many images you would need. And this depends on what? Yeah?
The time you have and what you have right now.
Yeah, it depends on how easy it is to collect this data, the time you have, but most importantly, it depends on how complex is the task. If it's, do I think that this task is complex for an algorithm or not? I don't think it is very complex for the most part, because lighter pixels are highly correlated with day. Darker pixels are highly correlated with night. So most of the pictures are going to be classified very easily by the model with 10,000 images. But if I wanted to work indoor, I would probably need 100,000 images, I would say. Okay, so 10,000 seems normal for outdoor, but indoor maybe a little more. Actually, for indoor, I think 200 images would even be enough, I would say, for outdoor. Okay, some of you have probably heard of splits. When you build a network, you want to build a data set, and you want to split it into train, validation, and test. Who's familiar with these concepts of train, validation, test? Okay, so just for those who are not familiar, usually you would train a model on a certain set, and you will test it on a set that you've never given to the model, in order to know how the model is going to perform in real-world tasks. Okay, so what should be the splits in this case? How much of these 10,000 images do you put to train the model versus to test the model? 70-30. Okay, who agrees with that? Okay, roughly, I think it's a good number, because this data set is not too big. If the data set is very big, you probably want to put 99% in the train and 1% in the test, if it's 1 million images. Because you don't need that many images to test the model. You just want a very distributed test set in order to test the model in every possible situation, especially for self-driving cars. Imagine how important the test set is for self-driving. Okay, what about bias? What do I mean by bias? Yeah, it's also called balance or distribution of the data set. You want to know, as you said, how much dark and like day and night images you have in the train set. You don't want to have only dark images in the train set, because the network is going to predict dark for everything. It's going to predict night for everything. You want a balanced data set, so that the network understands both what night is and what day is. Okay, input. images, we said. What should be the resolution of this image? And how do you choose that in practice in your work? The one the client gave us. Okay, next time we're going to tell something else to the client. Any ideas on how we choose a resolution for this task, for example? The higher the better, but it depends, and I'm repeating for the camera, but it depends on the input layer. Why does it depend on the input layer? Yeah. So you said in the end it's going to be matrices, so you will have to have 1 pixel per neuron in the first layer. That's what you mean, or per parameter in the first layer? So this is true for fully connected networks. It is not true for convolutional networks. So the advantage of convolutional networks is that the input image is not related to the size of the first layer. Okay? But there is a technique in order to choose this resolution. And what we do usually is that I will print an image, this image, that is, who found, what was that? Quand on s'en va bien, quand on s'en va, in the day. And so, what I would do is that I would print this image, literally print it on a page, and I would print it in different resolutions, like 40/40, 100/100, 200/200, and 500/500, for example. And then I would go and talk to humans, and I would say, tell me if it's the day or the night on these images. I will do it several times, and I will notice what's the minimum resolution that I can use in order to have maximum accuracy. You think we need 412 by 412 for this type of task as an image size? We probably don't need that many pixels. Actually, for this task, very few pixels are needed in order to compute if it's the day or the night. On the other hand, for face recognition, you think we need higher resolution or lower? Higher, because we need to see the details of the faces of the people. So the way you can do it is that you would print faces on images and you would ask people, can you tell if these two people are the same or not? And you would see how much you need in order to have maximum human accuracy. And then you would use that for your model. But the trade-off is between computation and accuracy. If the resolution is too big, the computation is going to be heavy. You're going to need months sometimes to train a model. If the resolution is smaller, then you can train quickly and iterate quickly to find out the right model that's going to lead to the best architecture and the best accuracy. Does that make sense? Yeah. So I think we can print this, and we will see that 64 by 64 by 3, which is considered small in Ukraine, is going to be enough in order to decide if it's a day or not. So we don't need more. So I reduce all my images into this size. Why 3? 3 channels, color. Do you think black and white would work better? For this task, black and white would probably be kind of hard. Especially because of sunrise, sunset, this type of thing that is not very clear if it's black and white. Output. What should be the output of the network? 0 or 1. Yeah, binary classification. What should be the last activation of the network? Remember on the previous slide we had a network and there was a neuron at the end. What should be this neuron's activation function? Sigmoid. Sigmoid is the function that takes a number that is real and puts it between 0 and 1. Why sigmoid? Because we want a probability between 0 and 1. Threshold bit decide if it's 1 or 0. Okay, so sigmoid, I agree. What architecture? Yeah, if you're fancy, convolutional neural network is going to be the best. But I think even a shallow network, convolutional or fully connected, probably convolutional, should do a very good job. You don't need a deep architecture. There's not too much complexity to build like on a human face, right? We just need to look at the colors mostly for this type of task. What loss function? This is a hard question for those who are not familiar with deep learning. Yeah, I heard it, I think. Someone said it. L2? L2 would work, but L2 is usually more used for regression tasks, where you want a real number. And we can talk about this reason, it's mathematical. But there is another loss function that we use very often in classification. Cross entropy. Binary logistic loss. Logistic loss also called binary cross entropy. So this is an ugly function, right? It's better to, like, this one is easier to understand. Y minus y, 1 minus y hat. It's the same idea. It's an objective function. If you minimize this function, it's the same as saying y hat should be close to y. That's what you want. It's a distance metric between y hat and y. And if y hat always matches y exactly, this function should be 0. Okay? So that's how it was designed. And then there's a lot more to discuss, and I'm happy to discuss that at the very end. Okay, so this was the easy example for today, just the warm-up. We're going to build on top of that and go now in face verification, okay, which is a little more fun. So now our goal, any question by the way on day and night? All good?
Are you going to explain at some point the difference in all the architectures?
I'm going to talk a little more about the architectures at the very end, yeah. We're going to look at an architecture for trigger word detection specifically. But feel free to ask questions if you want. So our new game is that we're a school, or even we're Sopra, and we want to use face verification to validate, okay, let's say a school wants to validate student IDs in facilities like dining halls, gym, and pools using face verification. So you know, when you go to the dining hall, you usually have a card that you swipe. And you swipe your card and it tells the machine that it's you. But the machine doesn't know if it's you. You can take the card of a friend and go and swipe it and go eat. But now it's a little more complex because you have a face verification, you have a camera looking at you. And the goal is that the camera matches the ID of the card. You get the problem? The camera is going to recognize you and say, is it the same person as the one on the ID? This is face verification. It's a little different from face recognition. What kind of data do we need, or does the school need to build that? Yeah. Okay, pictures of all the people in the school. That's true. Do you think we need pictures from people that are not in the school? Probably also. We want to tell the algorithm, these people, we should not let them in. Okay, so I would say we need pictures of every student labeled with their names. So this is Bertrand, for example. So Bertrand goes to a school, and Bertrand is in the database of the school. His picture is there, and his name is there. Okay? And this is true for every student of the school, but we're going to focus on Bertrand today. So this is another picture of Bertrand. So what's the input of the model? That's my question. When is this picture taken? Yeah, someone said? During vacations. I mean for this problem to work, where should the input come from? The camera, which one? At the cafeteria, yeah. So the input of the model should be the camera's picture. The camera takes a picture of Bertrand trying to get in. This is the input of the model that is going to output 0 or 1 probably, in order to decide if it was Bertrand. So yeah, what resolution? You don't know, you will try? Yeah, higher resolution. So I would say probably 412 by 412 is a standard resolution in face verification. And this is, again, we test it by showing to people. And really, like, I put an emphasis on that because it's better to spend a day going in the cafeteria showing pictures to people and deciding what the resolution is rather than taking it randomly and then having a network that trains far too longer. You lose, on the long run, you lose time if you don't do that. Okay, and the outputs were pretty easy. It's a classification problem. One, if it's Bertrand. So one, if this picture that is taken corresponds to the picture of Bertrand in the database. Yeah? 0 if it's not Bertrand. Okay. So Now I'm going to talk about architecture. What do you think should be the architecture to use here? And you can tell me a little more about the architectures you know about that would fit this problem. Give it a try. Try network. Convolutional network, probably because we know they work very well on images. I agree. Other ideas? Inception. Inception networks are a specific type of convolutional networks that work very well. Inception network is very likely to be used. It's a good point. So you probably read the FaceNet paper, maybe. Any other ideas? Okay. I think I agree with convolution, but there is another way to train these type of networks. So, the simplest architecture that you could use, right, could be, we have a database image, and we have an image of Bertrand coming in. What do? Simplest? Yeah. Someone said we take one minus the other. We just take the difference. Compute distance pixel by pixel. And you agree if it's the same image, it would be pretty low if you do the difference. If it's a very different image, it would be pretty high. So this is a very traditional way of doing it, very, very traditional. Why does this not work? Like, what are the issues with that? Orientation. If you just take the same image and like flip it or rotate it, it's going to give you a very high number when you do the difference. What else? Luminosity. I think luminosity is very important because pixels go from 0 to 255, depending on if they're white or black. So if there's a white pixel minus a black pixel, you're going to get 255 in absolute value. So in the picture, if like the gym is open at night, and the database picture is during the day, this method is not going to work. So, a lot of features. As you see, Bertrand is totally shaved here, but he has a beard here. It's a problem, because it's going to not appear in this distance computation. And then, a person can wear makeup, ID can be outdated, bunch of problems. So what we want is an architecture that will detect features of the face that are more important than just pixel-wise comparison. So like, what's the distance between the eyes? This is usually very important. Well, how big is the nose? How small is the nose? How big is the mouth? Where are the ears? What's the size of the head? All these features are important. And inception networks or convolutional networks are going to build on top of each other, all the neurons, in order to extract this meaningful information. And that's what we've seen earlier. You remember the slide where we said that later networks are going to receive information about eyes, mouth, and all that in order to decide if it's the same person or not. Okay, so I would say the solution we're going to adopt in this case is encode information about a picture in a vector. So I'm going to take the database picture, give it to a deep network that can be inception, or it can be another convolutional network, very well trained. And it's going to give me a vector, like that, 128 dimensions. This vector is going to encode information about Bertrand's face in the database. So now I don't even need to keep the face. I just need this vector. It encodes all the information. Now Bertrand comes, take a picture of him, give it to the deep network, get my vector, compare these two vectors in a distance. 0.4, it's less than the threshold that we decided. Y equal 1, it's Bertrand. If this is less than the threshold, it's probably the same picture. So, does this make sense or no? So this is very easy to say, but it's very hard to train. How do we know that this vector is going to be close to this vector? How do we know? We didn't train the model yet. Right now we're at the stage where parameters are pretty much random. We need to train the network in order to have these two vectors be very similar if the person is the same, and very different if the persons are different. Does it make sense? So now, the bigger question, once you understood that, is how do we train this network in order for this to be close to that if Bertrand is in both pictures? Okay, so this is the next question. How do we train this network? And by training, I mean the optimization we talked about earlier. Any ideas? Yeah. Yeah, pictures of many people. So let's say we have it. We have pictures of many people. What do we do with it? Okay, so a lot of pictures by the same person. Okay, so let's say we have 10 pictures of Bertrand. What do you do with it? You label it. So you say it's Bertrand? Yeah. Let's say we have 10 pictures of Bertrand and we know it's all Bertrand. Let's say we have 10 pictures of Bertrand and we have 10 pictures of Samantha. And we know it's Bertrand and we know it's Samantha. What do we do with it? Remember the goal. We want to create a network that takes an image and output a vector that should be always closed if it's receiving the same person. So, distance between what and what? Bertrand? Okay, so you're talking about computing a distance between Samantha's pictures and Bertrand's pictures? Yeah, and by computing a distance, I believe you mean the distance between the vector that comes out of the network. Yeah, exactly. So give it a picture of Bertrand, you get a vector. Give it a picture of Samantha, you get a vector. You want these two vectors to be close or far? Far, because it's not the same person. So you have to tell the model. So we have to build a loss function that does that, right? So let's talk about what we really want. What we want, and that's exactly what you described. We want the picture of two same persons to have similar encoding. It means the vector should be similar coming out of the network. If it's two different persons, we want the encodings to be very, very different. That makes sense? And this picture should be updated with the jersey. Forgot. So what we're going to do is that we're going to generate triplets. What it means is that we're going to take a picture of Messi here and call this picture encore. We're going to take another picture of Messi that we're going to call positive. And we're going to take a picture of Ronaldo and call it negative. Now, the question is, based on this, what do we want to do? We want to minimize the encoding distance between these two while maximizing the encoding distance between these two. Does it make sense? So we're going to design the loss function to do that by doing this. Enc of A is the vector that you get when you give anchor to the network. So how many dimensions is this? 128. This is the same thing for the positive image. 128 vector when it comes out of the network. This is enc A, and this is enc N, encoding of the negative pictures. Does this function make sense as the loss function? Yes. It makes sense because what it tells your model to do. It tells your model that if you give me a triplet that is A, P, N, anchor positive, negative, well, and the rule is always anchor and positive are the same people, and negative is another person. What I want the model to learn is that the encoding of A and P should be close to each other. So you want to minimize this term. And the encoding of A and N should be far from each other. So I want to maximize this term. Here is the answer. That tells the model that I want this thing to be very big because I want my loss to go down. The bigger this term, the smaller the loss. The bigger this term, the bigger the loss. So what I'm telling to the loss function is that I want these two to be close, these two to be far. Does this make sense? So this is how we build loss functions. Thinking what we want the model to do. Does this whole thing make sense, or do you have any questions? So let's do that. This is the network we saw earlier, and we're going to tweak it, because as I said, we can tweak the input, tweak the output, tweak the architecture. So if we tweak the input, instead of the picture of the cat, we have a triplet, APN. What is going to be the output of the model? I'm talking about the model, not the whole problem. What is going to be the output if I give it 3 pictures? Someone give it a try? It's not an easy question. The vectors, yeah. It's going to be the 3 vectors. You give the 3 images to the network. So it's going to give you 1 vector per image. Enc A, Enc B, Enc N. We're going to compute the loss function. This one. We're going to compute this value. And we're going to do the back propagation and update the parameters many times, in order for this to go down. So what we will do is this formula here, gradient descent, let's say, or another optimization algorithm. Doing that many times, at the end you're going to get this and this be close, and this one be far from the others. Does that make sense? So we've just built a phase verification system. And the whole part that was hard was to understand the loss function and the data set that we should choose. These are usually complicated. Okay, now we're going to tweak the problem a little bit, make it a little harder. We're going to go from face verification to face recognition. The difference is, now we don't have a card to swipe. We just have a camera. The camera has to say who you are. So it's harder, because before Bertrand could swipe, the camera should check and compare this image to the image in the database. Now it's different, no more swiping. You just have the image of Bertrand, you have to find that it's Bertrand. Or Samantha. So how do we do this? Knowing what we've just resolved. Can you use what we learned together in order to use the same network and perform the task? Yeah, that's true. We can have a multi-label classifier. So remember the one we saw earlier? We can have as many neurons as people in the school, and then we give it an image, and we have output the class that corresponds to the student. What's the issue with that?
If there is a new person, we have to learn again.
If a new person comes in, we have to learn again. I assume that Sopra is recruiting, and you get people coming in, and the schools are having a bunch of people coming in every year. So it's not possible to do that. Too much constraint. Yeah. Mm-hmm. Yeah, but we can use the same model. Yeah, that's true. So what we can do is called the k-nearest neighbor algorithm that some of you know, right? So what we have, as you said, is we have a database with pictures of Bertrand and every people in the school. But we don't have a swipe, so we cannot know which picture is this person that comes in. What we can do is to store a vector of encoding for all these database pictures. So all the pictures in the databases, we give them to the model, and we get the vectors that corresponds to everyone. Now, Bertrand comes in, you get a picture from him, you get a new vector, you will compare this vector to all the database. If there is a match, it means it's probably him. Does that make sense? What's the downside of this approach?
Someone is necessarily linked to a student database, not the database.
Yeah, I agree. let's say someone who's not in the database enters. We're going to compare this vector to everyone in the database. There's probably a chance that one person in the database is going to look a little bit like this person. So we have to define the threshold. And it's hard to find the threshold. We have to define it. It's very hard to say, like, if the distance is less than 0.5, then it's yes, otherwise it's no. There's a high chance that this person is going to have one picture that the distance is going to be less than 0.5. So what we can do is store multiple pictures of every student and compare it to k-nearest neighbors with different neighbors. We say if there is more than 3 pictures that have the distance lower than that from the same student in the database, then it's likely to be this student. Okay. Now let's tweak it again. Tweak the problem again. You want to do face clustering to group pictures of the same people on your smartphone. So you know, sometimes you take a picture and it tells you, oh, this was your mother, this was your father, this was your grandmother. It finds it for you. So how does it do that? We're not going to go into the details because it's a little more complicated, but maybe some of you have heard of this algorithm. Who has heard of k-means? Yeah, so it's a machine learning clustering algorithm. So now let's say you do k-means on the vectors in the database. If you do k-means on these vectors, it will cluster them by cluster. And your phone is the database. So you have tens of pictures of your mother, tens of pictures of your sister, your brother, and so on. And normally, the vectors corresponding to your mother should cluster in the same place, right? So you can use k-mean to cluster it. And then you get a new picture, you look which cluster it's in, and it tells you if it's your mother or your sister or your son or whatever. Okay? Does that make sense? Okay. And another question is, maybe we need to detect faces first. Let's say I take a picture from here, and I say, okay, do face verification. The network is going to be challenged because it's hard to find the face first. Networks is used to see very well cropped faces. So maybe you have to put a detection algorithm that will detect the faces, zoom on it, and then run the face recognition algorithm. Okay? Okay. How long are we? Around 15 minutes? 15 minutes? Okay, 15 minutes. Okay, so let's do some art generation. Art generation is fun. You give a picture to a network, you want to make it look beautiful. How do we do that? What kind of data do you need in order to complete this task? A lot of pictures? Pictures of what? The complicated part is that we have to define what beautiful is and what ugly is. And who are we to define that? So we cannot define that. But what we can say is probably a picture by a famous painter might be beautiful. That's it. So assume we have any data, and the input of the model is going to be 2 things. One is the content image. It's the image that you want to make look beautiful. So this is the Louvre Museum, and you're going to give it a style image. You want the Louvre Museum to be painted just as it was painted by, who's that? This is Claude Monet. So it's like, you want to get this image painted by Claude Monet, and you assume that this is beautiful. The output of the model should be something like that. Could be more beautiful, but it's fine. So what's fun is that you see the Louvre Museum, and now the buildings around it became flowers. The Louvre Museum itself became something that is greenish, like trees in front of it. So it's interesting because what we have here is that we kept all the content from this image. If you look at these 3 here, it was pretty big, but it's not here. So the content comes only from the first image, and the style is all from the second image. So the question is, how do you extract the content of an image, and how do you extract the style of an image, and mix them together? It's not an easy problem. So this is called neural style transfer. And the architecture we will use, I'm going to go a little faster because I'd like to do the last part, which is a little more interesting. We're going to go over the assumption that if we have a trained model that was trained very well, then given an image, if I look in the first layer, I should see the edges. If I look in the middle, I should see a little more complex archetypes. And if I go deeper, I should see very complex things, like faces, that fit on top of what was earlier. So let's assume we have an existing model that is a deep network that was trained to classify thousands of things. Very, very powerful network. I give it an image, it can tell me if there was a giraffe, a car, a flower on it, anything. So it works very well. If I look into this deep network, when we propagate this image, we can get the information about its content and its style by inspecting the layers. I can look in the layers and extract the content and extract the style. It's a complicated process, but assume we can do it based on the intuition that we have behind what layers contain, what we talked about earlier. So what we're going to do is that we're going to run the content image in this deep network. And we're going to extract some information from the neurons. This information, we're going to call it content C. Content of the content image, this image. We're going also to extract the style of the content image from the network. And this, we're going to call it style C. Style S is going to be the style extracted from the style image, and content S is going to be the content extracted from the style image. Okay, so we have four things. We have content C, style S, content S, style C, that are extracted from the network when we give these two images to the network. Okay, it will complicate. Again, the question is, what loss function should we use in order to get our mixed image at the end? And to go a little faster, I'm going to get back to a loss that is very similar to the face verification one. What is this loss saying? This loss is saying that we want the content of the content image and the content of a new image that I will call a generated image to be very similar. And I want the style of my generated image to have the style of my style image. So do you agree that if this loss is small, my generated image is going to have the style of the style image and the content of the content image? Yeah, problem. So let's see how this works in practice when we minimize this loss function. The main difference with this algorithm compared to others is that we're not learning any parameters here. We assume that the network we have is already good. So the deep network already has very good parameters. If I give it this random image to the network, and by pre-trained I mean the network is good. It's able to understand cats, it's able to understand humans, it's able to understand anything. So if I give it a face of a human and I look in the last layer, I'm going to see the face of the human in the last layer, and so on. So if I do that, and I compute the loss function here, do you think this number is going to be big or small? It's going to be very big, because this image doesn't look at all like the content of the C image, and the style doesn't look at all like the style of the painting. So I'm going to do the loop, and instead of updating my parameters, I'm going to go back to the input image and update the pixels of the input image in order to make this loss go down. So on this formula, instead of doing W equals W minus alpha derivative of the loss with respect to the parameters, I will do X input image equals X minus alpha derivative of the loss with respect to X, with respect to the input image. Okay? So that was all for our generation. I think we can move on to the deployment because this is a little less fancy. Do you want to do the case study on speech recognition, or do you prefer to go for the debate of what is an AI company? And the two of them are related, kind of. In preference? No preference? AI company? Okay. Okay, this had some architecture. We can get back to that later on if you want. Well, actually, this is part of AI company as well. Okay, let me go very quickly on that because it's very useful for AI company. So the task is given a 10-second audio clip. Detect the word activate. So I give you 10-second audio clip, and there is a bunch of words in it, like hello, bonjour, activate. And you want to detect if there is activate inside the clip. If there is not activate, you don't want to say anything. So this is typical like Alexa or OK Google. These are all trigger word detection algorithms. How do we build these things? Very interesting. Data should be a bunch of 10 seconds audio clips. We agree on that. What should be the distribution of these audio clips? It depends. If you want to learn every possible accent in the world, you need to have a very wide distribution. It gets very hard. If you want to learn a very specific type of accent, it's probably easier. You need less data. What's the input? A 10-second audio clip that is X, and we can represent it on a line like that. So this is a line that is 10 seconds, the yellow one, and there are two words that are negative in red. So negative words are words that are not activate. So this clip, if I have to do it myself, I would do like, hello, activate, bonjour, for example. So the blue one is the one we want to detect. The resolution, the sample rate is also a question you want to answer yourself, and answer before starting. I'm not going to talk about that to go faster. And what should be the output of the model? That's a very strategic answer. So you have an answer? 1 or 0, if activate is here or activate is not here. People agree with that? Okay, 1 or 0. I don't think that's the answer. There's a very big problem with that. So let me tell that. Let's say I ask, I give you a 10-second audio clip that is in Japanese. Any Japanese speaker in the room? Okay, perfect. No Japanese speaker in the room. So in Japanese, you're a machine, so you don't know anything right now. You're just given an audio clip, and you're given a label that is 0 or 1. Let's say I give you 3 data points, 3 audio clips, and 0, 1, and 0. Do you think you will be able to find out what's the correlation between the label and the audio clip? As a human, even. It's going to be hard. Maybe you're going to find, oh, okay, in the second audio clip there is this like a word that is not on the others. I think that's the one I should detect. But it's very hard. Right. So in order to improve this, we're going to give this to the model. We're going to give a sequence of zeros and ones indicating to the model where is the right word. If I give you that, it's pretty easy to find out what I want you to detect, right? I tell you, in the second audio clip there was 1 here, so you listen to this part, it should be the word that you're looking for. So this is a strategic decision that needs to be made up front. And there is a very big problem with this one as well. We can make it better. What's the problem with this one? It's very long. Yeah? What else? It's highly skewed towards 0. So it means the model, you're telling it to predict 0 almost all the time, and a little bit of 1s. So in order to balance that out, we're going to put several 1s for every positive word that we find. So as soon as we find a positive word, we're going to tell a bunch of 1s to the model in order to unskew the distribution of the data sets, the labels. Okay? This is a trick. What should be the last activation of the model? You know it, we saw it. Sigmoid. The difference is that the sigmoid is going to be sequential. It means that every time step, you want a sigmoid in order to predict between 0 and 1. If you think this time step is part of the word activate or not. Okay, architecture sounds like it should be a recurrent neural network, because this type of networks, they work very well on sequential data, which includes natural language processing, also includes speech recognition. What should be the loss function? Probably the same as we talked about earlier, the cross-entropy binary, but the difference is that it should be sequential. It should be at every time step, because we want to know if this time step contains the word activate or not. Okay, now what's very relevant to an AI company? This is an example of a technique we use, and it's a technique that would differentiate an AI company from a non-AI company. If you look at an AI team, they would do things like this, while others would do other things. So let's say we have to build this data set of 10-second audio clips. What I would say a company that hasn't done this before would do is that they would go out, probably, and label it, they would go out with a microphone, and they would ask people to say 10-second audio clips with positive words, negative words, and so on. So they gather a bunch of 10-second audio clips, and then they would label it, and then they would train a model on it. What's the problem with that? What can we have done better? So there's two things I think. One thing is a mechanical Turk approach. Do you know what is this? It's when you use a distributed way to label your data set. So you would use the cloud and send it to the Word so that the Word can label your data set. This is one way to do it, but I don't think the problem of this approach was the collection part. What we did was that we went out and we collected a data set using this process. I go with my iPhone and I ask many people on the Stanford campus to tell me activate. Just the word activate in a 1-second audio clip. I put all these activates in the blue database here. I ask them also to say negative words, random words that I generate on my computer. So I would go on a random word generator, I would click and I would say these 3 words. And I would get 1-second audio clips, approximately 1 second, with negative words, like lion, kitchen, whatever. And I would put it in the red database. So now we have 2 databases. Blue for positive words, red for negative words. What is the third one? Background noise. Yeah. Background noise is super cheap. You just go take the RR and put your iPhone on and you will get a bunch of background noise. You can even go on free license videos online and just get the noise, and that's all. This is super cheap database to build. What we did is that we synthesized data using the following process. We take a background noise of 10 seconds. We randomly insert between 1 and 3 negative words in this. And we randomly insert between 1 and 3 positive words in this. So you see, what's interesting is that if you do that, you can generate how many data points? Almost infinite. Infinite, actually. You can generate whatever you want. It scales exponentially with the number of positive and negative words that you have. So it's a lot stronger in terms of distribution than the method to get directly the 10-second audio clip and ask person to activate, kitchen, hello. It's a lot better to do that. What's the main advantage of that? We often say that labeling is the most costly thing in deep learning. What do you think is the labeling cost here? 0. Why? Because I know where I inserted the positive words. So I can say this is zeros, and when I insert the positive word, I put ones. So it's just a Python script of 30 lines of code is doing all my labeling. Does this make sense? So in one day, I can get probably infinitely much more data than the competitor just because I use this type of approach. This is the main difference between AI companies and non-AI companies, is that they're able to strategically collect and label data. They know it. They have the experience with that. Okay. There is an architecture search part. I don't know if you guys want to talk about it. But basically, what's interesting to get from that is, in order to solve this problem, you can get the audio clip that you synthesize, give it to a Fourier transform that is synthesizing speech, give the Fourier transform to an RNN, give it to a sigmoid, and get the distribution of the output. This is one way to do it, and I've spent weeks, maybe weeks, trying to fit a model like that on it to detect activate. It didn't work. I've tried everything. What made it work was that one day I was walking in the corridor at Stanford, and two of my friends are very good at speech recognition. They're doing their PhDs on speech recognition. They know that type of stuff. I ran into one of them and I started talking, and we discussed the problem I was confronting. And he told me, why are you doing that? You're crazy. Why do you think that's going to work? And I said, yeah, I think that's going to work. I searched online, there's nothing on speech recognition online. It's very hard to find. So what should I do? And he said, okay, you have several problems here. One problem is that this thing is too big. means the RNN, recurrent neural network, is having troubles understanding this long sequence. It's very long. You need to reduce this sequence. How do we reduce this sequence? After giving it to the Fourier transform, we use a convolution. What a convolution does is that it's given a large input and it reduces it in a smaller input. So I get now fewer time steps. He also told me that usually for this task, GRU is performing better than LSTM for this specific task. So I took it to GRU. He also told me that batch norm was very useful to accelerate training. I added batch norm almost everywhere. And I ended up with a model that worked. The issue here is that you get a much smaller sequence. So you cannot use your loss function anymore because there is no direct mapping between this length and the input length. So you need to expand it. You need to have an expanding post-process. So I tried that and it works. And so what I'm trying to explain here is that I would have not spent weeks if I had talked to this guy before. So it's very important to talk to the experts. And of course, you have a bunch of experts, but you don't have experts in every single category. Like nobody has. What we can do is contact people that write the papers. They're usually very helpful, especially if you're students. In companies, it's a little harder. But doing the search of the architecture by looking at what's done, what papers came out, what papers to read, is very important on the long run. And so what I usually do when I start a project is that I call a friend that is a specialist in the field, and I ask this person to give me 10 research papers that I should read. The 10 most important research papers that I should read. I spend time on this, and I choose which one I want to focus on that corresponds the most to my task. This is another thing, another process that we usually use. So never give up on the architecture, you can find it. And the last point is error analysis. In order to go from 97% accuracy on a task to 99%, it's very hard. And AI companies usually know how to do that. They know what is error analysis. So looking in the data, understanding what's the type of data that the network doesn't do well, add this part of the data. This is a lot longer process. How much more do we have now? Finished?
15 minutes.
15? Oh, 15 minutes.
Yeah, but 10 minutes.
Okay, 10 minutes.
If you have some questions.
So if I have to summarize the AI company points, I would say that the first important thing is strategic acquisition of labeled data. And Eldren is one of the first thinkers on what AI companies hire. And he's been building a lot of companies, so he knows a lot of this, a lot more than I do. Strategic acquisition of labeled data. So this is the example of the speech recognition data that we synthesize. Mastery of data interpretation. This is another interesting point that I would go. Mastery of data interpretation. So what is that? The example is, if you're a company that understands AI a little bit and you have a book recommendation website, so you want to recommend books to your users, what you can do is that you have a survey that the user fills in when the user comes, and based on the answers of this survey, you can recommend a book. So that's usually what has been done traditionally. When you walk in a bookstore and you see the person and you tell the person, I like fiction, I like that, I like this, the person is able to recommend a book. So this is the same thing online. Now, the level 2 is, you can get data from the user from the survey. You can also collect the cookies or other information on the user background if you have more information. You can build a model using all this information in order to recommend a book based on the user profile, a user profile that you store, right? And you know that a lot of companies use this to improve their recommendation systems. They compare the user profile to other users in order to know, this user looks like you, this user likes Hunger Games. You're very likely to like Hunger Games as well. So this is better than the first one, because they have user profiles, they understand the correlation between the background of the user and what they like, and they're able to recommend a book better. So this is the step 2. The step 3 is a little more complicated. Is the whole understanding of the concept of encoding. What's the concept of encoding? Is that an AI company was able to build encoding for almost every data that comes in and out of their system. every book that comes in. So a recommender, like I write a book, I wanna publish it, and I will put it on this book recommendation website. What the book recommendation website is going to do is that it's going to have an algorithm that is, let's say, doc to vec. It's going to read my book, put it in a vector. The book is understood. This is ideal. We're not there yet, but that's what would be a very good thing. They embed the information of my book in the book space. Every point here is a vector that encodes the information in my book. User space. Every point here is a vector, same as the one we saw with face recognition, kind of, that encodes the information about the user. And author space is the information about the one that wrote the book. What's the background of this person? And what's interesting here is that the company has a total understanding of what's the data that comes in and out. Every book that comes in, we can put it in the book space. Every user that comes in, we can put it in the user space. It makes it super easy, super fast to make the recommendation, but also to build other things. Now let's say I want to build a new product. My competitive advantage as this company is this book space. This book space is something I know and nobody knows. Things like that. This other space is something I know and nobody knows. I know what are the trends in books, what are the books that come out this year. Just look at the book space. There's a big cluster of new books here that are going towards that. There's a lot more information that this company is able to gather compared to the other companies because they have this automated process of understanding everything that happens. The user comes in, embedded in a vector, you understand which cluster it is in. You can recommend more information about this. Okay, so every user or book added to the website is automatically understood and interpreted by an algorithm. This is very strong. This is very hard to build, but good AI teams are able to do things like that. And finally, I would say that the last point is creation of sources of revenue using AI. This is a very technical point, but some companies have been great at not only supporting their core businesses with algorithms, but also going out and using their competitive advantage in a certain field in order to build new products. Let me give you an example. Let's say your company is selling books online. So not recommendation anymore, you're selling the books online. You can build data analytics to predict the demand, right? You can also use algorithm to recommend books to users. It's already pretty good. You know what demand is going to be, so you win a lot of money on the long run because you know we don't need to print 100,000 copies of this book because we know that the demand is going to be 10,000. Not bad. What an AI company that is strong can do is to build data analytics to predict demand, use algorithms to recommend books to users, but also build a digital book hardware that uses its partnership with ebooks editor to get digital copies of the book, acquire data on user reading patterns, and has now competitive advantage on the field. So what I mean is the competitive advantage they had on the field is not exactly about data. They knew that their competitive advantage was to have connections in the book space. It means they knew a lot of authors because every author was selling book on their platform, right? So what's interesting is that they realized that why don't we go digital and we use just one email to all our 5,000 book editors to just send us PDF instead of sending us books. That's all. That's the only difference. And now editors send book online to this company. This company builds a hardware that probably doesn't need to be a high technological piece, sells it, and gets all user data on this hardware. Everything you read. Every pages you go back, you go from. So a lot of meaningful data that they can use later. So they realized that there was something that was related to their competitive advantage as a bookseller, not necessarily as a data. It doesn't come from any algorithm, it just comes from realizing that there is this opportunity by the fact that we know all these people in the book space. We're the best ones to create a book, a digital book hardware, and get data quickly, spread it, and collect it. So I think very good companies are able to support core businesses with AI, but also create new sources of revenue using AI and using the data they acquire through these digital hardware. Okay, I think that's all. Yeah. But thanks everyone. Sorry it was very long.
this is working, and this is working.
Oh wow.
So it's a little weird, but this is a box that we're going to throw you now. If you have some questions. So go ahead, raise your hand if you have a question for Kian, and I'll throw you the box to the mic. We're very modern here.
It's the first time I see that.
So what's the question and what's the box in the face? One question over there. So it's going to be a long throw. So be careful.
Nice.
Thank you. My question is, how did you recognize the style of the picture in one of your examples?
Yeah. In the neural style transfer. Yeah, let's go back quickly in this one.
Yes.
So how do I recognize this thing?
Yes.
This thing. It's very interesting. But does anybody has the answer or no? So what's interesting is that content seems easier than style to find. Because as we saw on the example I previously showed about the faces, you can get the edges from the content. You can just look in the activations of a layer and get these edges. But the style seems harder, and the reason the style is harder is because the style, in order to get it, you need to forget every localized information on the picture. You don't want any localized information, you just want to get the style. You don't want the localized information. So there is a technique called a gram matrix. I don't know if you've heard of it. It's a basic matrix transposition. So if you multiply a matrix by its transpose, you unlocalize the information of the matrix. It's called a gray matrix. And this technique is used in order to extract the style. So there's some math behind it, and we spent like about a week on the deep learning specialization course to explain these two things. So I would say, I wouldn't have time to explain it all, but look for gram matrix and look for neural style transfer.
Okay. Thank you.
And feel free to ask questions in French if you want, because I know the technical words are.
So I'm asked some questions. So we talk a lot about explainability in deep learning. Can you explain what it is and how that works?
Oh yeah. So there's a lot of debates on explainability. Like one weakness, or what people think weakness is from deep learning, is that we cannot explain where this prediction comes from, which is true in many cases. We don't know why the network knows what's happening. So let me give you an example actually with a cat classifier. Where is the, oh, here. Can you see what's written on the board? Even in the back? Okay. So let me give you this example. We have an image.
If you have like a,
Oh,
like a
So I give you an image that is an image of a cat. So there's a cat here in the image. Right? There's a cat here. And the cat is given to a network that is very good. So I would call it the very good network. The very good net. This network is going to output a number y hat that is going to be between 0 and 1, but probably, because it's a very good network, is going to be close to 1. Now, someone comes to you and say, oh, explain this network. How do you know it's seeing the cat? Like, what proof do you have? Explainability. Can someone explain why this network works? Or a way to show that this network works? Any ideas? Basically, what you want to show is that the network is not looking here in order to find the cat. It's looking there. So there are many ways. One way is you take a black box, you put it here, and you hide the pixels from this part. You give this new image to the network. You see what's the probability the probability you get. Then you move the square here. Same thing. Move it, move it, move it, and so on. And then you will get somewhere here. if you give this image with the black box here, do you think this probability is going to go down or up? It's probably going to go down. And by looking at the probability map of this image with the squares, so what was the y hat probability when the square was here? What was the y hat probability when the square was there? And so on. If you look at this, you should see that the highest probabilities y hat are everywhere but here. Does it make sense? This is called occlusion sensitivity. And it's one way to interpret a network in vision, for example. It's not a very good way. Why? Because you have to run so many times the image in the network. It doesn't worth it. Also, the square should be smaller or bigger. There's many different things you could do. So there is actually one very fast way to do it, is to compute this number. What is this number? What's the interpretation in terms of words of this number if you have to describe it? The interpretation is how much should we move x, the input image, in order to have y hat move, right? And what's the shape of this? This number is a matrix of the same size as the image. If it's a 3D image, it's a 3D matrix. So the shape of this thing is the same shape as the shape of x. And now, the numbers you should get here, you should get higher numbers for pixels that are part of the cat. Because these pixels, if you move them, it should change the probability a lot more than if you move this pixel. If I move a pixel here, it's not going to change anything about my y hat if the model is looking at the right space. So if I just compute this simple number, I can get what we call a saliency map and decide where the network is looking at. There are many ways to explain neural networks. It's not perfect, but I guess a very famous example that's been used, I think, by Kian is that we flew a plane before we understood how they fly. And we're using neural networks in many things on our iPhone. Why we don't fully understand them, but we try to understand them better. But there are techniques. I'm happy to talk about the papers or give you pointers on what papers you can read in order to get more information about explainability of neural networks.
Thank you. Do we have another question?
Okay. You said we asked people to know the resolution of the peak. But why don't we take the human resolution? Like, can we say, like, computer can be better, and so we take the lower resolution?
Sorry, you mean why don't we? So let's say we test the resolution and we get that 400 by 400 is a good one.
Yeah.
You mean why don't we take a bigger one or a smaller one?
Smaller, like instead of 400, why don't you take 300?
So you're saying, why don't we say a computer is going to be better than a human, so we can give a lower resolution, it's still going to find the answer.
Yeah.
That's what you're saying?
Yeah.
Someone has the answer? So do you know about human level accuracy, Bayes error, or all these things?
A little bit.
So let's talk about that. Let's give an example in healthcare. In healthcare, there's a famous problem that is chest x-rays. I give an x-ray, and I want an algorithm to look at this x-ray and tell me if there is a pneumonia. It took me time to pronounce this one. Pneumonia on the x-ray. What happened is that they gave it to a lot of radiologists. That one radiologist would label all the images. And everything you do, the network is not going to do more than 97%, let's say, if you train it on this type of data set. The reason is the radiologist does 3% error. So you see, the model is given 3% of the images wrongly labeled. So it means 3% of the images, you're teaching wrongly the network. You're telling the network that there's no pneumonia while there was a pneumonia. It's just that the doctor didn't see it. So the issue is if you have a too low resolution and the labeling was done by humans, if the labeling is wrong, then the network is going to be wrong because it's going to be taught wrongly. There is another way. It's you can be labeling the images with high resolution and reduce them when you give them to the network. In this case, you could test lower resolutions for the computer because you believe that if the images were labeled by a group of humans instead of one human, then you have a higher chance of having the computer beat the human. So it's the same thing. In healthcare, computers today, they do better than one doctor, but they don't do better than a group of doctors labeling the images. Because they were taught how to learn by a group of doctors instead of being taught how to learn by one doctor. Every chest x-ray that is hard to understand by a doctor, they're going to discuss it. And they're going to decide all together what's the ground truth. And that's why computers are often better in some tasks.
Well, thank you. I think it's really for right now. So we're going to move on to the cocktail hour, the best hour. And then we're going to talk to Kian if you have any more questions. Thank you very much. Thank you.